on YouTube at the end. But all the materials that I use is in a Google folder. So you can just go on my website. The link is in my bio, and you can find that on the Google folder. Okay, let's make sure it's recording. It's recording. All right. So welcome back. We're going to be talking today about functional groups, right? So we've really kind of, spent a lot of time talking about bonding. We've talked about bonding patterns, how to draw Lewis structures. So imagine you know how to draw a Lewis structure, right? We went through a formula, we put our atoms together, and we showed that we could draw reasonable structures with different degrees of unsaturations based on our calculation from the little formula I gave you. And these are molecules that potentially could have come from a particular formula, right? And what we're going to do now is to transition from just drawing structures and seeing if we can start identifying units within structures. Because these units that are within structures will tell you how these molecules are going to react. And we call these functional groups, all right? And so functional groups are really specific atoms that are bonded in a certain arrangement, and that gives that compound or that portion of the compound certain physical and chemical properties, all right? And so if you can identify these features or these combination of atoms, you can then have an idea of how this molecule is going to react. And so what I'm going to do today is I'm going to tell you what these functional groups are, and we're going to hopefully practice identifying them. But before we jump into these functional groups, what I want to show you is line angle formula, right? So we have been spending a lot of our time working on just drawing atoms directly, right? So for example, I will draw this molecule here on the top of the page, and I'm going to show you what it looks like in our Lewis structure. Okay, so this is the analogous Lewis structure for the molecule that I have on the page, the first molecule on the top. And this is something you could have drawn if I'd given you a formula, right? And you would have figured out that this formula is what? C3, right? Three carbons. We have 5, 6 H's, and we have 2 oxygens, right? And this here would have been a potential formula you could have drawn. And I already see that I've made a mistake in this molecule. My apologies. There is no extra methyl here. So we need to modify this structure. That is not acetic acid. Let us modify this structure to make it look correct. This is what I actually wanted to draw for you all, which would have been C2H4O2, all right? That's what I wanted to draw, C2H4O2, okay? So I could have given you this formula and you would have drawn something, and this would have been one of the potential structures you would have drawn, okay? Now, as I mentioned to you all at the beginning, the very, very first lecture, we talked about the fact that we don't like to draw all the carbon atoms because as the molecules get larger and larger, we'll be writing C's and H's constantly. And so we have to find a shortcut to draw very large organic molecules quickly. And what we do is we use these line angle representations. So if you notice, you see a bunch of lines in these molecules, but those are really carbons. We like to represent carbon as a point. And so that could be a carbon. This could be a carbon. That would be a carbon. This would be a carbon. So if I saw a molecule like that, right, which is the same thing as just writing that, then what that tells me is I have 4 carbons in this molecule, okay? So that's a quick way of drawing 4 carbons in a row. Now, you might say, where are all the atoms, the other atoms? The other atoms are implied. okay? Particularly hydrogen atoms are implied, I should say. Let me correct myself. Hydrogen atoms are implied. So we have to know something about the bonding of these atoms in order to know what's implied. And carbon makes 4 connections. Remember, we've hammered that out for the past 2 lectures. Carbon makes 4 bonds. So any bond that is not shown is expected, right, or suggested to be to an H, right? It's implied that it's to an H. So for example, let's take this carbon in the molecule. I can see clearly that that carbon I've dotted here is connected to 2 other atoms, and they are carbons. This carbon is connected to a carbon on the left and a carbon on the right. Does that make sense to everyone so far? Good. What that means is I've made 2 connections to carbon, but I know that carbon must make 4 bonds, okay? And if carbon must make 4 bonds, then where are the other 2? And this is where the implied bonds to hydrogen come in. If I don't see the extra bonds that make it up to 4, then I'm going to assume that those bonds are to hydrogen atoms. And that's kind of what we do. So this is a hydrogen, and this must be to another hydrogen, which would round out the molecule or the carbon atom to having 4 connections. Does that make sense? So anytime you see atoms that are not drawn in, you should assume that they are connected to hydrogen to make out the octet. So that would mean this carbon here on the bottom left, it as shown, it's connected to 1 carbon, which means it must have 3 more connections to make 4. So there are 3 hydrogen atoms that must be connected to that carbon, okay? And we can go through the rest of the molecule and we can figure that out. So for example, how many hydrogens are connected to that carbon that I circled? 2, correct, right? And what about the one on top right there? How many hydrogens are connected to that? That one would have to have 3 exactly. So it's implied, and it makes you able to draw molecules very quickly because you're not drawing the hydrogens and you're not writing the C's. You can see every time it bends and there's a point that you have a carbon atom. Okay, so now that I've introduced line angles to you, let's see if we can appreciate the fact that the C2H4O2 molecule that I drew on the top right is identical to the structure I have next to it on the left, the line angle, which is acetic acid in vinegar. So you can see from the regular Lewis structure on the right, I have 2 carbons. And if you look at the line angle, I have 1 point and I have another point. Does that make sense? And so that is 2 carbon atoms. That's consistent. Now, the carbon on the bottom left only has 1 connection. And so it's implied that it must have connections to 3 more atoms, specifically hydrogens. And if we look on the right, we can see that that carbon atom has 3 hydrogens attached to it, okay? Now, this is where things get different, all right? Where we do things differently. If the atom is not a carbon atom, we have to write it out, okay? So because oxygen is a non-carbon atom, if there's a connection to an oxygen, we have to write out the O, as you see we did here in the structure, and we write out the other O as well. Now, one last rule. If a hydrogen is attached to a non-carbon atom, you have to write it. The only hydrogens we do not write are hydrogens that are connected to carbons. So this is why this O has an H written, because hydrogens attached to non-carbon atoms are written out. Does that make sense to everyone? Any questions? So let's follow the rules again. Let's go back through. Number 1, carbon atoms are represented as points. And so every time the line bends, there is a new carbon atom there. Number 2, hydrogens are implied, meaning if a carbon atom is showing 1 connection, 1 bond, then it must have 3 other bonds to hydrogen atoms if it is neutral. If it wasn't neutral, we would have written a charge. And finally, any non-carbon atoms, if they have hydrogen atoms attached to them, you must write the hydrogen atom next to that atom. And so this is why we have this structure. Okay, so now that we understand line angle drawings, why don't we pivot back to functional groups? So as I said, you can draw a structure, but a functional group really is a specific arrangement of atoms, right, combined together that give a compound these particular physical and chemical properties. And you're going to have to identify them. And what I've shown you here are 5 acids. And acids, right, these are 5 acids, by the way. And these acids, I picked these 5 acids for a reason. These are the 5 common acids in wine. I actually have a glass of wine right now next to me. So that's what came to mind when I was putting this together. So these are the 5 common acids in wine. And if you look at them, you can see that they all have a particular arrangement of atoms in common, right? So we're identifying our first functional group. And that is this unit. That unit is present. That unit is present. This acid has 2 of those units. Does everybody notice that? Yeah, that's our carboxy unit or carboxylic acid unit. And how many carboxylic acid units are present in the next molecule in tartaric acid? Can someone tell me how many units they see in tartaric acid? 2 carboxylic acid units. There they are. Okay. And how many are in citric acid? 3. Very nice. So we see 1 here, 1 here, 1 here. So what you have all done just now is that you were able to look at all these molecules and identify a unit we call a carboxylic acid unit. And the name tells you its function. It's an acid. So whenever I see this unit, I know it's acidic. All right. And hence the reason why all of these molecules have the name acid at the end. Acetic acid, lactic acid, malic acid, tartaric acid, citric acid. Okay. So another functional group right here below is a very common one. This is called an alcohol. Okay. And alcohols have just an OH group attached, right? And that is different from a carboxylic acid. Let's draw it out. A carboxylic acid has this unit. Okay, carboxylic acid. Meanwhile, an alcohol has just an OH. It does not have, right, the C double bonded to O in it. An alcohol doesn't have the C double bonded to O next to the OH. And that's a very big difference, right? That's what makes it an alcohol versus our carboxylic acid. And here are some alcohols you know. Ethanol, right? Everybody knows ethanol. Isopropanol. This particular alcohol is present in rubbing alcohol, right? That's what you use it for. And then we have another alcohol here. This molecule has 2 alcohol units, 1 here and 1 there. And this is called ethylene glycol. And ethylene glycol, you can find that in antifreeze. You can find it in brake fluids, right? So this is a pretty common alcohol that people use a lot. So hopefully you get the idea of how you can recognize these units. And what I'm going to do now is let's look at a lovely organized list of different types of functional groups. Now, what I'm going to do right now is I'm going to zone into each area. And what I've done here for you is I've categorized them. There are a lot of functional groups, as you can see, and we're going to walk through them. I've categorized them for you. And the first category is the category of hydrocarbons. And the name tells you what kinds of atoms are present in this functional group. Hydrocarbons mean hydrogens and carbon atoms. So these functional groups are really made up exclusively of carbons and hydrogen atoms. And that's why if you look at the structures, you don't see any other elements. I don't have any O's, oxygens, I don't have any nitrogens, I don't have any sulfurs, no other elements. It's just all straight lines. And remember, each line is a point. And so the very first functional group within this category is that of an alkane. Alkanes are just all carbons single bonded to each other. So here is a carbon again. I'm emphasizing the fact that these are all carbon atoms, right? That is a 1, 2, 3, 4, 5, 6, 7 chain carbon alkane, right? And if you were to name this, we'll talk about naming eventually, you would call this heptane. This is heptane. And you know other alkanes. Octane that you put in your car, right? For your gas, right? When you buy your 87% octane, that would be 1, 2, 3, 4, 5, 6, 7, 8, right? That's 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. This is a molecule you put in your car for as gas, right? Now you know the name, now you know the structure, you can draw it. It's just a molecule with 8 carbon atoms. The next, and we can talk about another one like butane. You all know butane that you use. That's 4 carbons. Propane for your propane tanks for cooking. That is 3 carbons. And methane is 1 carbon, right? For methane gas. So these are all compounds that you're very familiar with or potentially familiar with. The next category are cycloalkanes. All these are just alkanes that are in a ring. So instead of the alkanes being in a line, they just end up circling back on the original alkane, original carbon. So they're just in rings, okay? An alkene means that there is a double bond present in this molecule. And so you can see in this alkene, and I'm giving you the degrees of unsaturation in these molecules. We could calculate them, but we can also see them, right? So here's an alkene unit present in this molecule. Once we have a C double bonded to C, that's an alkene. And then we have an alkyne, that is a C triple bonded to a C. And now we have a special kind of hydrocarbon. I really love this. This is probably my favorite. This is called benzene. Benzene is a 6-membered ring with 3 double bonds in it. So benzene looks like that. You can never miss it. It is just a six-membered carbocycle with 3 double bonds present. So a lot of names I know. This sheet is on the drive. You can print it out and you can just learn them, okay? So let's move on to another category, oxygen. So what happens if you have an oxygen in the molecule? So we've already talked about one of these functional groups. Once we have an OH, we call that an alcohol. And let's be careful. The OH must not have a C double bond O next to it, because if it does, then that's a carboxylic acid, right? Here is another functional group. This is a specialized one. This is what we call a phenol. A phenol is really an alcohol plus benzene, okay? So it's benzene with an alcohol. So it's benzene and an OH. You can see it here. Here's the benzene. Here's the OH. Together, they give you a new name, and we call that a phenol. All right. And next is an ether. Ether is an oxygen in between 2 carbons. And we drew that before. I mentioned that in the last lecture. So this is an ether. If you see an oxygen in between 2 carbons, it's an ether. Now, I know some of you all are probably getting overwhelmed. Please do not. You have this cheat sheet. Just use it. We're going to just use that eventually. If you take organic chemistry and become an organic chemist or a serious organic chemistry student, you'll see these functional groups over and over and over again. There are only so many of them. And then you just become accustomed to them and you can recognize them pretty quickly. All right, next we have an epoxide. This is just a 3-membered ring. So it has to be a 3-membered ring with an oxygen. Okay, so if you have a 3-membered ring with an oxygen, 2 carbons and an oxygen, that is an epoxide. So 2 C's plus 1 O. Right? That gives you an epoxide. All right, and then alkyl halides. Alkyl halides just mean you have a halogen in the molecule. Yes, actually, I like that. Ether does look like a face. And so here we have The actually, I think ether looks like a bat to me. It's like a bat. And alkyl halides are really just halogens attached. So if I had a carbon chain with a bromine or chlorine, these are alkyl halides. You just need a halogen that's attached. All right, we're making our way through. There are two more categories, and then what I'm going to do is I'm going to test you. So take screenshots of these, or you can go to the Google Drive, and there's a folder that's called, a file that's called functional groups, and you can pull it up. But you're going to need the screen, and I'll pull out again. So for those who want to take a screenshot and look at it. So next up, we have the ones that have nitrogen atoms present in them. These are amines. Amines are just a nitrogen atom with carbons or hydrogens attached. Remember, nitrogen must make 3 bonds. So that nitrogen can be attached to 3 carbons. We call it a tertiary amine. If it's attached to 2 carbons, we call that a secondary, right? So you can see there's 3 carbons here. So attached to 2, we call it a secondary. If it's attached to 1, we call it a primary. Don't worry about that for now. Imines is when there's a C double bonded to the N, and the nitrile or cyano is when there's a C triple bonded to an N. A lot of things to remember. All right, my final category is the carbonyl category, is what I like to call it. This is the most important category for me. I love this category. It has really, really awesome functional groups that you can recognize. And so how you can tell that you're going to be in the carbonyl functional group category is the C double bond O. They all have this C double bond O. If you have a C double bond O, it's going to be one of these down here, right? So carbonyl is not a functional group, just to remind you all. This is not a functional group. It's just a unit that other functional groups have, okay? It's not a functional group, just a unit that other functional groups have, and it's this unit. So how do we recognize all the functional groups that have this unit? Well, it really just depends on what's on either side of the C double bond O. Remember, carbon makes 4 bonds. So if it's making 2 bonds to oxygen, it must make 2 bonds to other things. And so depending on what those 2 are, that gives you the functional group. And so for aldehyde, if there's a carbon on one side and a hydrogen on the other side, that gives you an aldehyde. So it doesn't matter what else you have. If there's a carbon on one side and a hydrogen on one side, that's an aldehyde. So if X equals C and Y equals H, that gives you an aldehyde. A ketone, you need a carbon on one side and a carbon on the other side. So if X equals C and Y equals C, we call that a ketone. A carboxylic acid, you already know this one, right? There it is. If there's a X equals C and Y equals OH, okay, then that is a carboxylic acid. And now an ester looks very similar to a carboxylic acid, but if X equals C and Y equals OC, if you notice, this O is attached to a C. And then finally with amides, if X equals C and Y equals N, right? That gives you an amide. So these are how you recognize. I know this is a lot, but I'm going to give you all a test next week. By the way, I've decided your first exam is coming up next week, all right? So get yourselves ready. I'm going to post an exam, and you're going to have to know. So Ashley, I see you asked the question, what X is. X is just related to this structure that I have up top here. So all I have is just a design for you to recognize the molecules. So it's just really what's on the left and what's on the right. That's all I'm saying. So X is what's on the left or what's on the right. That's what those are, okay? So are you all ready to practice? Let me zoom out for you all. If you want to take a quick picture of the screen. So for those who want to look at the names of the functional groups, and I'm going to give you 10 seconds to do that. And after that, what we're going to do is we are going to identify some functional groups. Zoom back out. Let me zoom back out for a second. Yes, there we go. Remember, this document is on the drive. So if you have another device, you can go on my website that is linked in my bio on the live, or for those who have been following, you should be able to have access to that. And then here's the other page. Are we good? Are we ready to practice? Yes? Are we ready? All right, let's see. Let me pull up another file. I have a bunch of molecules. And what we're going to do is we are going to see if we can identify. Let's start off with penicillin. This is the structure of penicillin. And what I want you all to do is to see if you can identify any functional groups. By the way, I wrote this as CO2H, but I really should have drawn it out. So this should really be C double bond O OH. I think you all know what functional group that is already, right? That's what CO2H is. Let me write that up here. CO2H is equal to C double bond O OH. That's what CO2H is, okay? Everybody got that? Okay, so let us practice. Let me see if you see any functional groups. I see some names people are putting some names out. So far, so good. You guys are good. I really love the guys. It's a very smart class. I'm gonna have to give you all some more difficult ones. Okay. So I see some very good answers in the chat. So yes, there's a benzene ring right here. I mean, there's a color, a different ink to identify. So we see a benzene ring there. That is a benzene, very nice. I also see people pointing out that we have a carboxylic acid right there. That's a carb acid. I'm going to shorthand it and write carb acid. Any other functional groups? So I saw someone said there's a cycloalkane. There isn't a cycloalkane here. And the reason why there isn't a cycloalkane is because all the atoms in the ring have to be carbon. Benzene is a cyclic system with all carbons, but it's a specific one. The other rings in penicillin, they have a nitrogen atom in the ring. And so you cannot have a nitrogen or any other atom in the ring to call it a cycloalkane. It has to be all carbons. Okay, I see amide. There's an amide present. How many amides are present? 2 amides. Yes, I see someone write that. So there's an amide, and here's an amide. And remember, what I'm looking for, let me go back. What I'm looking for is, here's my carbonyl unit, right? I'm looking for the atom to one side is a carbon, and the atom on the other side is a nitrogen. And once again, for this carbonyl, one atom on one side is a nitrogen, and the atom directly attached is a carbon, right? So you need a carbon and a nitrogen on both sides. And that's the giveaway for the amides. Very, very nice job. We have 2 amides here. Okay. All right. Let's move on and let's do Viagra. I had to find a very funny molecule. So let us see. There isn't anything else going on in this molecule. You could, let's pause for a second. You could call this an alkane. We're typically not going to call alkanes out as a functional group because alkanes are going to be part of most molecules. Okay. The CO2H isn't drawn out. That's a shorthand version. Sometimes we shorthand it as CO2H. As I told you all before, when you see CO2H, this is really what it is. So I apologize, I should have drawn it out, but that's just habit. We oftentimes just shorthand it and write it like that. Okay. Let's look at Viagra. I'll give you some time once again to to figure this one out. Now, this one is very heavily nitrogenated, right? So I'm giving you a molecule that has a lot of nitrogens in it. So you kind of have to look for your nitrogen functional groups. So let's take some time to see if we can identify our nitrogen functional groups. You all are such very good students. You all make me very excited to do this. I'm having a lot of fun with you all. Okay, I see some good answers in this. All right, so let's talk about some functional groups. So some of them will be a little bit tricky, so I'm gonna kind of stick to the simple ones. So do we see any functional groups in this that we recognize? I see people saying there are imines. Yes, you could call this an imine and you could call that an imine, right? Do we agree? There are C double bond ends. Any other functional groups? I see amine in the chat. Yes, we have a nice amine right here. This is an interesting amine. It has a sulfur attached. I wouldn't ask you that in a test because we haven't talked explicitly about sulfonamides, but we'll leave it to the simple one. Any others? Benzene, yes, I see a benzene. Let me write the names for you all. So this is an amine, and we have imines. And I see someone pointed out that we have a benzene. Yes, very nice. What else do we have? Ether. Yes, I'm glad someone saw that. Here is an ether. Remember, ether is oxygen with two carbons next to it. There are the two carbons that I'm highlighting. So that is an ether. Very nice. And there is one more, one major one that yes, you do need to spin it around we have an amide, people, an amide. There is an amide present. Here's the amide right there. That's an amide, right? So we have a nitrogen with a C double bond with a nitrogen on one side, and it also has a carbon on the other side, okay? So it is like playing I Spy. It really is. That's kind of a good way of thinking about it. All right, I'm not done with y'all yet. Let's look at chlorophyll A. Yeah, let's look at chlorophyll. This is a structure of chlorophyll. Why don't the magnesium makes it tricky, but I do like this molecule. But let's look at chlorophyll. Let me adjust this camera a little bit. I think it's right. Okay. So yes, it's a lot. This one is a lot. There's a lot going on in this molecule, but we got to practice. I have to make you all good students. You're not going to leave my lecture not being able to identify your functional groups. You're going to be functional group experts after this lecture. Okay, so there's a lot in this molecule. So let's go through. I see alkenes. There are so many alkenes in this molecule. Here are two alkenes that we can highlight. There's there are a lot of alkenes, right? So we have alkenes. I want the fancier ones. Someone else said alkane. Yes, we have a big alkane chain all the way around here, actually. So we could say that that's an alkane. But so that's an alkane. Ooh, what did I just do? I just erased my molecule, part of my molecule. Oops. So yeah, this is an alkane. What is this? Oops. Alkane. All right. What else do we have? I see. Oh, good question. Someone is asking me what does the dashes mean and the wedges. You notice you have darkened lines and dashed lines. That is talking about the three-dimensional structure of the molecule. We're not there yet, so ignore those. Think of them as straight lines for now, okay? Think of those as straight lines. Excellent question. Those are explaining the three-dimensional, like where they're pointing in 3D space. We're not there yet. That's above our pay grade for today. All right, so Esther, I see Esther, I agree. There, how many Esthers do we have? How many Esthers do we have? Anybody? I actually see two. Here's an Esther. Remember, you need a C double bond O. Let's be careful. I'm going to go through the other one. This is a C double bond O. Next to it is an O attached to a C, and on the other side is a C. This is also an ester. Does that make sense? You have to be careful. This is an ester. We only have two esters. But let's look at the other C double bond O, because we have another C double bond O. Remember, when you see C double bond O's, you don't know which functional group it is. So you kind of have to evaluate what's on both sides of the C double bond O. So here's my next C double bond O. What is on the left of the C double bond O here? That's a carbon. What's on the right? It's another carbon. So it is a ketone. Okay, so be very careful when you label your carbonyls. That is a ketone because you have carbons on either side. Okay, so you could say there are imines here as well. Okay, you could say we have imines. Here's an imine. Here's another imine, etc. Okay, but I think you all get the point. You're identifying the functional groups. Some of the, I don't really like the ones that have, you know, like other atoms in them, but nonetheless, we will do that. Why is this on my screen? I don't know what this box is. So ignore that. Okay, so what do you see in this one? Let's do this one real quick. We have benzene rings in this one, right? So benzene. We have an imine in this one. Here's an imine. And we have an amide in that one. Let's use a different color. We have an amide in this one. Sorry about that box. This is an amide, okay? So, or an amide. And we have an halide. That's a phenyl halide. But yes, we have that. So very nice job, everyone. Give yourself a round of applause if you can identify these functional groups. I am very, very, very impressed. Okay, so we're going to go back to our lecture because we have some, as I promised, we are going to move on to start talking about reactivity. This is where the fun starts happening, right? We've introduced a lot. Now we have to start drawing reactions. We have to start learning how these functional groups react with each other. And I want to teach you all about arrows and electron pushing arrows. So let's start off with our definition of acids. If you go back to high school, right, or in general chemistry, oftentimes, people give you the Bronsted-Lowry definition of an acid. And they're like, what is an acid? An acid donates a proton, right? Anybody remember that definition? Yes? Say yes if you have, yes. And a base accepts a proton, right? Those are the definitions, okay? So that's a specific type of acid, and there are lots of acids that operate in this way, right? We have sulfuric acid, hydrochloric acid, nitric acid, right? All of those acids are classic Bronsted-Lowry acids because they will be giving up a hydrogen. And then our bases that we're used to is like sodium hydroxide, right? Sodium bicarbonate. Like those are some bases that we're accustomed to. So why don't we draw then an acid-base reaction that shows the reaction between an acid and a base, and how, as an organic chemist, we like to draw and represent how these molecules are interacting with each other. So here is a very simple acid, and I'm going to start off with acetic acid. This is an organic acid. We know this functional group, and I'm writing out the atoms this time, just for this example. I'm writing out the atoms, not doing the line angle. I'm going to write out the atoms. And I'm going to put all the electrons in. So we're going back to square one. right? How we would have drawn this. We're happy with this molecule. This is a weak acid indeed. We can label this as the acid. And we know it's an acid because it has the name. But how else can we tell it's an acid? An acid is a molecule, as by the Bronsted-Lowry definition, that's going to donate a proton, okay? There are 4 protons or hydrogens in this molecule. And I'm going to tell you right now that only one of these protons gets donated. Only one of them. And how do you know which one is getting donated? Which one? And you can take a guess. There are 4 hydrogens or protons in this molecule. 3 of them are on carbon, and there's 1 on oxygen. How can you look at an acid and decide which hydrogen is the one that's going to be donated from that molecule? So I see some comments about the one bonded to oxygen. That is correct. But my question for you is why? Why is it that one? I see it in the chat. Yes, a very high electronegativity difference. Remember now, let's go back to electronegativity. Electronegativity is the atom's desire to pull electron density to itself, right? So when we see 2 atoms in a bond or a relationship, it doesn't mean that it's an equal relationship, right? And so if we remember our periodic table, the elements on the far right and up, those elements are very electronegative. They are pulling electrons to themselves when they're in a relationship with another atom. And what that means is that can tell us about the strength of that bond. If one atom is really pulling electron density towards itself, then that bond is going to be weak, right? And so the OH bond is weak, meaning the hydrogen is grasping for those electrons that the oxygen is holding on to. And as a result, it's going to be very easy to pluck it off, right? To entice it away from that molecule. Meanwhile, carbon and hydrogen, their electronegativities are very similar. If you look at the values, the electronegativity for hydrogen is about 2.1, carbon is about 2.5, oxygen is about 3.5. So hydrogen and carbon, they have a similar electronegativity, which means neither of them are really pulling the electrons from each other. They're more sharing these electrons, right? But oxygen is really, really pulling those electrons towards itself, which means that bond is really, really weak. And so it's going to be very easy to pluck that hydrogen off, which makes that hydrogen the acidic hydrogen. Does that make sense to everyone? So when you look at a molecule, the easy, quick, shorthand way of deciding in the acid which hydrogen you're going to take or which one's going to be donated, however you look at it, it's always the hydrogen atom that's in the worst relationship or the one that's connected to the most electronegative atom. That is a very simplistic way of thinking about it, okay? Now, let's look at our base. So I'm going to react this with sodium hydroxide. Sodium hydroxide has an ionic bond and it has a covalent bond. The O and the H are covalently bonded to each other, and the sodium and the oxygen are ionic bonded. They are electrostatically attracted to each other. So this is the base. So how do you know something is a base? We just talked about an acid. The acid, we're going to see a hydrogen in a very poor relationship. The base, we typically will see a negative charge on an atom, okay? Okay, so therefore, we can identify most of our bases. Most of the ones we'll use for simple reasons will be an atom that has a negative charge. It's electron rich. And so these molecules, the acid is going to react with the base. So the atom that's going to get the H in the base is typically the atom that is rich in electrons. And let's talk about this from a relationship perspective. All right. So we're going to focus on the relationships. This is the relationship we're looking at. That OH bond has quite the relationship, right? The relationship is bad. The hydrogen is suffering. The oxygen is hogging all of the resources of the electrons, right? And so the hydrogen is looking for a better relationship, okay? So what can it do? Well, the oxygen in the base that's negatively charged, it is electron rich, right? It is rich in electrons. You can see it is negatively charged, right? It has a formal charge of minus, which means it's rich. It's rich in electrons. And you can see the lone pairs. It physically has 6 electrons surrounding it, okay? Which means since it is rich in electrons, it can share its electrons with the H. It can be like, hey, hydrogen, I know your oxygen boyfriend sucks and is taking all of those electrons, pulling them towards itself. Why don't you share 2 of mine with me? Okay? And so that's exactly what's going to happen here. And so really, we can draw that. And as organic chemists, we love to show how these things happen. We love to show how the bonds are broken, and we love to show how the bonds are formed. Okay? And so let's do this. All right. I'm going to draw this really properly. This is a very, very, very important concept in organic chemistry. And you have to really understand how to do that. Remember, they travel in pairs for now, the electrons. And so we are going to draw what we call a curly arrow or a curved arrow. And a curved arrow looks like that. Okay. We're showing an arrow. And let me explain what this means. It's directional. It shows you where electrons are moving. So if I have a pair of electrons, it's showing me that those 2 electrons are moving from that location to that top of the arrow is that location. The other thing we do with the arrows is the number of barbs on the top of the arrow tells you how many electrons are moving in this process. If I drew 1 barb on the left, I would be telling you that I am moving 1 electron, okay? Now, because I drew 2 barbs in this one, I am only moving 2 electrons, okay? Does that make sense? Everybody follow that? So that is what's going on in this case. All right, so let's draw the result of this reaction. I'm going to draw the products down here. And I'm going to show you how it happens. So what's happening now, let me put my arrow in color so you can see. I'm going to erase this. I'm going to erase the blue so it's not in the way. Okay. So what's happening here is that the oxygen with the electron, the rich oxygen with the electrons is going to say, hey, I'm going to share my 2 electrons with you, right? So that arrow I just drew showed that the oxygen is sharing its 2 electrons with that hydrogen. Does that make sense? Everybody follows that along? Okay. So what does that mean for the hydrogen? Can the hydrogen accept these 2 electrons and just accept 2? How many electrons can hydrogen have in a relationship at any given time? What is the max number of electrons? 2 electrons. We talked about that. Oxygen can only have 2 electrons at a time. So if hydrogen. So if hydrogen is accepting 2 electrons from a foreign oxygen, the neighbor across the street or the milkman, however you want to describe this oxygen, what would it have to do with the electrons that is currently in a relationship with the oxygen? What does it have to do with those 2 electrons? Can you hold on to them? You have to break the bond. You have to let it go, right? You have to let it go. And so this hydrogen then, and where are the electrons? Remember, every bond is 2 shared electrons. Remember that? Every time we see a bond, it's really 2 shared electrons. So what we're going to say here is that this hydrogen is going to let go of those 2 electrons, and it's going to give them up to that oxygen. Does that make sense? Any questions? These arrows describe clearly what is happening in this relationship building and relation and bond breaking. It's bond forming and it's bond breaking process, right? So the oxygen on the right is sharing 2 electrons of the hydrogen, but in order for that hydrogen to accept those 2 electrons, it has to let go of the 2. And the 2 electrons it currently is holding on to is the 2 it's sharing with oxygen. So let's draw the result of that. What does that look like? So that looks like a hydrogen, okay, that is now on the other side. And this oxygen just gained 2 electrons. The 2 electrons it was pulling and pulling away from the hydrogen, it finally got them, right? It got them. And this would make it have a negative charge, okay? And the good question, what happened to the hydrogen? I'm going to write this plus over here for a reason. The hydrogen is now in a relationship with the other oxygen. Right? There it is. This hydrogen is this hydrogen. It's now in a relationship with the other oxygen. And the 2 electrons that the oxygen shared are here. They're in the bond in between the oxygen and the hydrogen. And you made water. Now, the question you should be asking is what happened to the Na? The Na now ends up next to anything that has a negative charge. The Na is going to just hang around with anything that has a negative charge so it can make an ionic bond. And the negative charge on this side of the equation is that oxygen. This is a classic Bronsted-Lowry acid-base reaction with what we call a mechanism. Yes, the sodium is going to go with anything that's negative. Any questions about this? Do you all want to try one on your own? All right, let's try one on your own. I'm going to switch this up for you and give you one that's a little bit more challenging, perhaps. I'm going to give you a base that actually doesn't have a negative charge. But I'm going to label it as a base and label it as an acid so that you can figure it out. So here is a hydrogen atom attached to a chlorine. This is clearly going to be the acid. We agree? We have a hydrogen attached to an electronegative atom. This is a very toxic relationship. Yes. And I'm going to give you a base. This is the base that we're going to use for this reaction. Okay. And this base is going to be neutral. Okay. But you can clearly see which atom is going to be sharing the electrons from the base. Okay. So based off of this, I want you to draw me the arrows of the base reacting with the acid. Remember, the acid-base reaction is effectively an atom with a lone pair. Typically, it's negative. That's going to be the base. And that atom is going to share its electrons with a hydrogen that's in a toxic relationship in the acid. And that atom will have to give up its electrons. And we can draw the chlorine electrons if you want. I know they're there, but let's practice this. I'm going to give you a minute to draw this. And then we're going to end with this. And I will put some in the drive for you all to practice. And yes, you might see me writing this equilibrium arrow. This reaction is in an equilibrium potentially. We're not making any conclusions yet. So we're doing that. We can determine the direction of this equilibrium, but we'll save that. Okay, I see some people say that they're done. So people are on top of this. Are we ready? All right, can someone tell me which atom is going to be sharing its electrons with a hydrogen that's in a toxic relationship on the left side? Which atom has electrons to share? The nitrogen, right? Yes. The nitrogen has electrons. I drew them in for you. So the nitrogen is going to share the electrons with the H. But if the H accepts the electrons, what does it have to do as a result? What does it have to do? Give the electrons that it currently has to the Cl. You all get this. You see the pattern, right? You see the pattern? This is literally the pattern of an acid-base reaction. Once you've figured it out, it's the same thing over and over again. Okay? Now, let's see if you could actually draw the products properly. Let me see if you drew the products properly. So what's going to be what's going to be left over here? We're going to have Cl minus, right? The Cl finally got its electrons, which means it's going to be negative. And the hydrogen is going to migrate because it just made a new relationship. It left the Cl and made a new relationship with that nitrogen atom. Okay. You notice I never touch any of the atoms that I didn't involve in this process. All the atoms that I didn't involve in this process remain where they are. So based off of this, do I need a charge? Because you all know your bonding patterns now, right? Should there be a charge on any of these atoms? Always check if there's a charge. My carbon is making 4 bonds. That's good. I say yes for nitrogen. What should the charge be for nitrogen? A positive. Very nice. And how do we calculate it? Remind me. The valence electrons minus the number of sticks minus the number of dots. There are 4 sticks, but there are no dots. So that's a +1, right? And that's why we have a plus on the nitrogen. Okay? All right, you guys did extremely well. We are going to stop here for today. Next, we're going to look at Lewis acids next time. We're going to talk about, Lewis acid, Lewis base. We're going to refine our understanding of acids and bases. And then we're going to move on to some really, really fun stuff that I still need to figure out which direction I'm going to take this. So thank you all for joining again. Once again, your homework is online and you're doing really well. So thank you. Have a good night, everybody.